Okay, so welcome to this fourth video in linear programming. In the first videos, where we started was we started with the very natural formulation of our linear program, and then in the subsequent videos, we progressively manipulated that format to arrive at a much more convenient format of our linear programs, which is this format here, which we called standard equality form. And so this came from the prior video. And so in standard equality form, every linear program we showed could be written as a maximization of some linear objective function, given with some matrix constraints, where all the matrix constraints were equality constraints, and we had variable constraints, which was every variable had a non-negativity constraint, and that was it. And so everything could be written in this form. This is a convenient form because it's going to help us show properties of linear programs. But to get there, we're going to need to develop some notation, and so this video is going to be about such notation. And so specifically, we'll be talking about submatrices and subvectors. That the notation for these things is what we want to discuss. But we're going to start by first finding not just any, we're not going to maximize this objective function yet, but we are going to find vectors x such that we satisfy all the constraints. Those are called feasible solutions. They're not necessarily the best, but at least they're feasible because they work. They satisfy all these constraints. And to find feasible constraints, we're actually just going to focus on these matrix constraints for now, and later we will see how we can also satisfy these variable constraints. But we start here because linear algebra helps us figure out what's going on here. We know that from linear algebra, ax equals b has a solution x if and only if b is in the column space of A. And so we're actually going to be talking about the columns of A quite a bit. And that's where the notation is going to come from for these submatrices and subvectors. So here's an example of such a matrix A, and I've indexed the columns from 1 to 6. In general, we know that the column indices start from 1 and go up to n. Now, if I take, let's just take some random subset of the indices, j, we'll call it. So j is a subset of the indices 1 up to n. Then A sub j, this will be the submatrix of A, which corresponds to the matrix formed by just taking the columns of A that are indexed by j, and just sticking all those columns together in the order they appeared, and that matrix is what A sub j is. So for example, if j equals, let's say 2 and 4, then A sub j is going to be the second and fourth columns. So the second column is 1, 0, 0, and the fourth column is minus 1, 2, 1, minus 1, 2, 1. And so that's the matrix A sub j given this set of indices j. Similarly, we can also talk about the subvector. X sub j, we know that the vector x consists of, in this case, 6 components, 1, 2, 3, 4, 5, 6, of course, same as the number of columns of A. And so x sub j will consist of the components of x that are indexed by j, again. So it'll just be 2 components. It'll be x2 and x4. And in both situations, the indices appear in the same order that they did here. So for instance, these columns, first 1, 0, 0 came, and then minus 1, 2, 1 came, and so similarly here. All we're doing is we're just highlighting the particular columns that are relevant and squashing them together in that order. And similarly for the vector x, we just highlight the components that are relevant, squash those together. Okay, but we don't care in general about random subsets. What we care about is going to be subsets of these indices that correspond to bases of the column space of A. So column space of A is a vector space, and so every vector space has bases, of course. And in particular, we know some bases of the column space will come from exclusively from the columns of A itself. That's, by definition of what the column space is. Okay, so let's notate it by B. So B will be a subset of indices 1 to up to n, such that the columns indexed by B form a basis. That's what we want, a basis of the column space of A. Okay. So this isn't unique. There's lots of possibilities. Let's just take a look at one or two of them. So here's one example. So say e.g. B could be how about 2, 3, and 5. So the second, third, and fifth columns of A, these columns form a basis of the column space of A, and that's just by intuition from linear algebra should tell you that's true. Just one component here, one non-zero component here, and then in this third vector, the only component that hasn't appeared does appear here. So anyways, it's obvious from linear algebra that this is in fact a basis of the column space of A. And so we're actually going to conflate the idea of a basis of the columns with the basis we'll also call B, which is the set of indices, we'll also call that the basis. So we'll conflate the indices corresponding to the basis with the name basis. So I'll say B is a basis, even though I don't mean that the indices 2, 3, and 5 are a basis. What I really mean is the columns that correspond to indices 2, 3, and 5 form a basis. But forget about that technicality. We're going to make a new definition saying that B is a basis when the indices correspond to a basis. Okay, one other example. How about 1, 5, and 6? Just so you can see that there's many possibilities here. 1, 5, and 6. Again, for similar reasoning as before, it's very obvious that this is also a basis of the column space of A. Okay, so let's write A times X. What is A times X? Well, that's a linear combination of the columns of A, and the combination is given by X. So in other words, I can write it like this: j equals 1 to n of x sub j, a sub j. So in our case, let's say a times x equals x1, a1. I don't really want to write all these out. Let's just do the compact notation here. J equals 1 to 6 of x sub j, a sub j. And let's continue working. So let's continue assuming that our basis is 1, 5, and 6. Let me write that somewhere else. So over here, the basis is 1, 5, and 6. Sorry, one other piece of notation. Let's say that a capital N will be all the indices, so from 1 to n, without B. So it's the rest of the indices, in other words. So in this case, it'd be 1 to 6 without 1, 5, 6. So in this case, it'll be 2, 3, and 4. It's just all the indices except for the ones that were in B. So 2, 3, and 4. Okay. So x sub j, a sub j, that's a sub j is, by the way, if it wasn't already clear from context, it's the column of A indexed by j. So this is the jth column of A. And we're just taking the linear combination of the columns of A. That's what A times x is. And so let's now split this up. It's just a sum of these linear combinations of these columns. So I can write this as x1, a1 plus x5 a5 plus x plus x6 a6 plus, now I'll write the rest of them, x2 a2 plus x4 3 x3 a3 plus x4 a4, like that. And so let's view this as this is this is the following. So this is the sum of xj, aj for the j in the basis, 1, 5, and 6, and this is the sum of the j in n, the indices j and n, of x sub j, a sub j. So all I've done is I've just separated out the basis indices linear combination from the non-basic indices linear combination, and we can do that. And now using our new notation, this is the same thing as AB XB. Okay, so AB is the submatrix of A indexed by the columns B, and X sub B is the subvector of X indexed by B. And similarly, this is AN XN. Darn it, there we go. AB XB is here. It's the submatrix of A indexed by B. Same thing for X, subvector of X. And this is ANXN, which is analogous, but for the indices N instead. And so and in general, this applies. What we've just shown is that A times X equals ABXB plus ANXN. And we actually didn't need B to be a basis in this case, but it'll be relevant that we're talking about bases and not some other random subset of indices later on in a subsequent video. But for now, this is the fact that I wanted to show, and we can express this with our new notation that we got from submatrices and subvectors. And that's actually it for this video. We're going to use this notation to start talking about relevant properties so that we can find solutions to AX equals B in subsequent videos. But that's it for this video, so thanks for watching.